Okay. So, so this x omega, okay. So once you apply Fourier transform, okay, uh, so you will have x omega. This x omega is a continuous variable. This n is a discrete variable, okay, and you can find the x omega by doing adding the summation from minus infinity to plus infinity, okay, using this summation, okay. But once you apply, if you want to convert this x omega, this frequency domain signal into time domain signal, okay, into time domain signal, that is by applying inverse Fourier transform, okay. So if you want to apply the inverse Fourier transform, this of x omega, so you can't get the simple summation because this omega is a continuous variable. It is not a discrete variable. Okay. So there you need to do a integration. Okay. So if you apply the inverse Fourier transform, so inverse is denoted like this: inverse Fourier transform x omega, that is the this frequency domain signal. Then you will get the time domain signal mxn. Then, but you have to do a integration from within 2 5, that means within one period, x omega e to the power j omega n d omega. Okay, so here you need to apply a integration because this omega is not a discrete variable, it is a continuous variable. Okay. And we have found, we have done, I think, as I can remember, we have done several examples related with Fourier transform. It is not much difficult. Okay, so the so the convergence of Fourier transform is not much difficult because if we have a finite value, we called it the Fourier transform is converge. Okay, otherwise it is not converge. Okay, so it is very simple, but it is not like in Z transform. Okay, so you need to have, you in Z transform you need to find where this Z is converge. Okay, the convergence value you need to find, but with respect to Fourier transform, that is no need. Okay. So, so you no need to care about the energy density spectrum of non-periodic signal. Okay. Uh, Another example. Okay, so maybe you can do this part only. Determine the Fourier transform of this signal. Okay, so maybe you can try to find this. This is not much difficult. Okay. Uh, okay. So if I just quickly do it, so what you need to do, apply the Fourier transform. If you need to find the Fourier transform, okay, for this one, for this question, okay, so that is xn. Okay, I will quickly do this example. Xn is equal to a and 0. So this a is 0 with respect to n. So within n, between 0 and l minus 1 and 0 otherwise. Okay. So this is the signal we are given, a periodic signal, and we need to find the Fourier transform here, discrete time Fourier transform. Okay. So we will see how to do this. Okay. So so just you can use the basic principle to find. Okay, so if we draw the signal, it is like this. Okay, if I draw this signal, it is like this. Okay, we have n and we have xn. Okay, so n is starting from 0, no? Okay, 0 and l minus 1. Okay, so 0, 1, 2, 3, like this up to l minus 1. Okay, so that value will be a. Okay, so it will be a like this. Okay, so this value will be a. Okay, otherwise 0. So other minus 1, minus 2, and up to it will be 0. And the here L plus 1, L plus 2, up to infinity. Again, this is 0. Okay. So our sequence is only here, up to here. Okay. So what is the length of this sequence? Can anyone tell what is the length of this sequence? What is the length of this sequence? How many values are there? If I write xn, okay. So A, 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 like this, how many values are there? This is 0 and this is L minus 1 value. Okay, so how many values are there? What is the length of this sequence? What is the length? Yes, that is L, no? Okay, so the length is L. For example, if you have a 9 value, if you have 9 here from 0 to 9 value, 0 to 9 value, that means there are 10 value, no, including 0. Okay, so 0 to L minus 1 means there are L number of terms. Okay, so this length is L. Okay, so what you need to do is, okay, you need to apply the uh, uh, Fourier transform to xn. Okay, so you need to apply the Fourier transform to xn, so it will become x omega. This is the frequency domain signal, and you need to get the simple summation. Summation is from n from 0 to up to L minus 1, no? L minus 1, because others are 0. You need to get the summation. All other one will be 0. So if you get the summation from 0 to L minus 1, that will be enough. Okay. And you will have xn e to the power minus j omega n. Okay. So then you can find, you can expand this. Okay. So once you expand this, you will have here when n is 0, x0, that is a, e to the power 0, so that will be 1, plus x1, that is also a, e to the power minus j omega, plus a, e to the power minus j dekai omega, 2 omega, plus a, e to the power minus j 3 omega. So on, you will have a, e to the power minus j L minus 1 omega, no? Okay, so these are the terms. Actually, this is the x omega. Okay, so if you have done your work up to here, that will be enough. Okay, so here you can get this a value. Okay, then you will have 1 e to the power minus j omega plus e to the power minus 2j omega plus e to the power minus 3j omega, so on, up to a e to the power minus j L minus omega. No, sorry, this a is not there because we get the a here. Okay, so actually if we get this e to the power minus j omega as x, no, so this series will be somewhat like 1 plus x square plus x3 plus x4 up to x L minus 1. Okay, so this is a power series. This is a power series, and you can find the using the power series uh, identities, you can find the addition of these sum up to L minus 1, or maybe you can use the Taylor series here. Taylor series, no? Yes, I think I have explained how to use the Taylor series to find this kind of signal. Okay, so using the Taylor series or the power series expansion, you can compact this you can find the compact expression for these terms. Okay, so these are distributed terms now. Okay, so you can find the compact terms. Okay, so should I do that one? I think it will be okay, no? Okay, so I think maybe you can remember that Euler formula said that a plus a square plus a3 up to infinity. Okay, so what is the value? 1 into a minus 1 or something. No, I can't remember exactly. Okay, so maybe we can see it. Uh, Taylor series, Taylor series, Taylor series, Taylor series. One minus x, no? Okay. So you need to get this one actually. You need to guess this one. Okay, 1 plus x square plus x3. 1 divided by 1 minus x, no? Okay. Okay. So here, okay. So here, sorry, this is not 1 minus a. Okay, so you have this one, and if you multiply this, so this is xl minus 1, no? If you multiply this series in al, so you will have al plus al plus 1 plus al plus 2 plus al plus 3 up to again infinity. So that will be al 1 minus a. So if you subtract 2 from 1, okay, so 1 minus 2, if you get 1 minus 2, okay, so you will have these values, okay, a plus a square, a3, so on. Okay, so here again you have al minus 1 plus al plus al plus 1. Okay, so these terms will be cancelled. Okay, so and you will have only up to here a l minus 1, so it will be 1 minus a into a l 1 minus a, so it will be 1 a l into 1 a. Okay, so this is the compact expression. Okay, so this compact expression using so you can convert this expression to a compact expression using this Taylor series. Okay, so I think that is clear. Okay, uh, so that is how we find Fourier transform. Okay, so likewise. Okay, and I think there are some properties related with Fourier transform. Okay, I think we have done some properties in Z transform. Okay, okay, Z transform properties we have seen. Okay, so the same properties are the ours. Okay, so here you can try to find the Fourier transform of these signals. Okay, so these are very simple actually. Okay, so you are asked to find the Fourier series of un. Okay, so it is goes up to infinity, no? Okay, it is goes up to infinity, so you will have the term like 1 plus e to the power minus j omega plus e to the power minus 2j omega plus e to the power minus 3j omega. So that up to infinity once you find the Fourier transform of un. Okay, so this is again Euler formula, so you can compact this one to uh, that compact form. Okay, so maybe you can try to find very easily. Okay. Mm. Okay, so try to find the uh, Fourier transform of this signal. Actually, this un. So you can see that cos omega n multiplied by un. So that means cos omega n is starting from 0 to infinity, okay, because this un is from 0 to infinity, no? Okay, so here this one also from 0 to infinity, and other one will be cancelled, okay, because there is the un exists from 0 to infinity, okay. So the minus infinity 0 value will be cancelled. Only 0 to infinity will be there. Okay. So when you get the summation, you need to get the summation from 0 to infinity. Okay. So try to do these questions. Okay. And I think okay, this one also somewhat important. Okay. So I think it is better if you are familiar with one or two properties of Fourier transform. Okay. So I think it is not much difficult. You can do this by yourself actually. Okay. Here we have this is the table. Okay. So you can use this table. Okay. So I think this you can understand what is here. Okay. So if you have x n value, if you find the x omega, okay, and if we get the conjugate of x, this indicate the conjugate. Okay. So the conjugate means uh, so this is the complex value. Okay, this is the complex signal, a plus iy type signal, or e to the power a e to the power minus j omega n type signal. Okay, so if you find if you know the Fourier transform of xn, and if you get the conjugate means the plus value here. Okay, if xn is e to the power j omega n minus j omega n, x conjugate will be plus j omega n. So you will have the conjugate but minus omega. Okay, you need to get the conjugate of the Fourier transform, then you need to replace omega by minus omega. Okay, so these are maybe not much important. Okay, I think there are the others. There are other properties also. Actually, this one, okay, this one is the properties of Fourier transform, discrete time Fourier transform. Okay, and you can see the notation here. If the signal is xn, the Fourier transform will be x omega. If the Fourier x1n, Fourier transform will be capital X1 omega, x2n, capital X2 omega. Okay, and this is the linearity property. I think you are familiar with this one. Okay, because in linear time invariant system also this kind of condition should be satisfied. Okay, so if if there is two signal added with weightage, okay, so that signal, the Fourier transform is the signal also can be added with the same weightage to find the Fourier series of this composite signal. Okay, so that is somewhat important. I think this one also very important, time shifting property. Okay, so it is like this. Okay, it is like this. If we know, I will write it here. Okay, time shifting property. Okay, and it is like this. Okay, if xn Fourier transform is x omega, okay, if xn Fourier transform is x omega, and if you shift this xn by k, okay, so this is a shifting. Okay, so shift maybe this is a delay shift. Okay, if minus, it is a delay shift, signal is shifted to this side. Okay, and if it is plus, it is advance shift, that means the signal is sequence is shifted to this side. Okay, So if you shift the signal, then Fourier transform will be e to the power, I can't remember exactly, e to the power minus j omega k x omega. Okay, e to the power minus j omega k x omega. Okay, so it is minus k. Here also it will be minus omega k. Okay, so x omega should be multiplied by this value. And if it is plus, x omega should be multiplied with e to the power plus j omega k value. For example, okay, so you are find the value of xn, no? Xn is this one. If I ask you to find the value of xn minus 5 something, that means with the, from 5, all these series shift into this way. Now it is starting from 5. Okay, it is starting from 5 somewhere here, a like this up to uh, uh, L values. Okay, so that means 5 plus L minus 1 value there. Okay, should be there. Okay, up to this point, this sequence is expand. Okay, so so you need to know, you no need to find it again, because you know the Fourier transform of this one. Okay, so that is this. Okay, that is this. Okay, actually a is nothing but e to the power minus j omega. Okay, so xn, Fourier transform of xn is 1 minus e to the power j omega L. Okay, because L is here. Okay, because L is here. Okay, divided by 1 minus e to the power minus j omega. And if I ask you to find x n minus 5, then you no need to find it at the beginning. Okay, so you can simply multiply this value. This is x omega. Okay, this is x omega, multiply by this e to the power minus j omega. Now k is 5. This term 1 minus e to the j omega k, 1 minus e minus j omega, like this. Okay, and if you ask to find x plus n plus 5, so this will be plus. Okay, so you no need to find it at the beginning. You can simply find, multiply this omega by plus or minus j omega k. That is simple. Okay, so that is time shifting property. Okay, that is time shifting property. And the time reversal property is here. Okay, time reversal property is here. That is also simple. Okay, so time reversal means if you have xn value, that is like this, here, 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 like this, up to L minus 1. And if you get x minus n, that means you need to get the image of the x-axis, image of this signal on the x-axis. So your signal will be here, come from here up to this side, from up to minus L minus 1. Okay, up to minus L minus 1. That means minus L plus 1 up to. Okay, and if you find the, if you ask to find the Fourier transform of this time reverse signal, again you no need to find it at the beginning. What you need to do is, okay, so you have already find the Fourier transform of xn, that is 1 e to the power minus j omega L, 1 minus e to the power minus j omega L. Then what you need to do? Okay, so simply you need to apply omega minus omega instead of omega. Okay, so this omega will be minus omega, so this will be minus omega, so this will be plus, and this one also, this is minus j omega, no, this omega also will be minus omega, so this will be plus. Okay, so easily you can apply the apply the find the Fourier transform of that property. Okay, so if you ask to find the x minus n, the time reverse signal Fourier transform, then how we find? So this is the xn, this is xn, okay? So x minus n Fourier transform will be x minus omega. So what you need to do, instead of this omega, you need to apply minus omega. So you will have 1 minus e to the power minus j minus omega. So that means j omega L, 1 minus e minus j omega, minus j minus omega, minus minus again plus. So you will have j omega, this one. Okay. So that is the time reversal property. And this convolution property is also very important. Okay. Maybe you have to apply this one. Okay. Why this is very important? This is very important. Why? Because you can see that this convolution become a multiplication here. Okay. So this one is very important. This property actually we are using much to analyze LTI system. Okay. For example, okay. So you know that for LTI system, okay, LTI system, that means linear time invariant system. Okay, linear time invariant system. Okay, and if you apply a input signal xn, okay, there is a output signal yn, okay, and there is a impulse response hn. Impulse response is one, if you apply a impulse here, the output due to the impulse, that is the impulse response, okay, and if you apply delta n, the system will output you the hn. So this will be the impulse response, okay, and this is the characteristic of this system, okay. So the output yn can be written as xn convolution hn, okay, for LTI system, okay. And if you are given yn, okay, and so maybe, so if you have a filter here, let's say that this is the filter, so you can apply a non-series xn, then you can measure the yn also. Okay, so you can measure the yn, you know the xn, but still you can't find the hn. Why? Because this is a convolution, so you can't do the inverse convolution, it is not possible. Okay, so what you need to do is you need to apply Fourier transform. Okay, so if you apply Fourier transform, this yn become time domain signal y omega, xn become xn, this hn become xn become x omega, hn become h omega, then this convolution become a multiplication. Okay, now you can find h omega y omega divided by x omega. So if you know this, you can find the Fourier transform y omega. If you know this input signal, you can find the frequency domain signal x omega. Then if you divide y omega by x omega, you will have the h omega. This is normally we referred as transfer function. No? This is the transfer function of the system. Okay. And actually this is in frequency domain. So we called it frequency transfer function. Frequency transfer function. When you are designing a filter, this frequency transfer function is very important. Okay. So you can easily find the h omega. Okay. And what you need to do if you find the time domain transfer function. Time domain transfer function we referred as hn. Okay. So hn, if we apply Fourier transform to hn, so it is the transfer function h omega, frequency transfer function. And if you want to find the hn using this one, h omega, what you need to do? You need to apply inverse Fourier transform to this h omega. Okay. Then you can find this hn. Okay. So it is very important. Okay. Very important. This one. Okay, for example, okay, I will give you to do one example, so try to do this. It is not much difficult one. Let's say that you have the Hn, okay? Hn is, let's say that 0, 1, 1. This is the Hn, okay? And you have an input signal Xn, okay? You have the input signal Xn. So this is your input signal Xn, and you have the Y output signal Yn as 1, 1, 1. Okay, this is your output signal. Okay, and if I ask you to find Hn, how you find? How to find this Hn? Then what you need to do? You need to apply Fourier transform this to 1. Okay, so that is very simple. You need to apply 0 to 1 to 0 to 2 xn e to the power minus j omega n. Then you can expand this. So you can have a value here. Then you can find yn. Okay, so what you need to do? Okay, so this one is also 0 to, let's say that this is the 0th value and this is the 0th value, 0 to again up to 2, 0, 1, 2. Okay, and that is yn e to the power minus j omega n. So if you expand, you have that term also. Okay, so what you need to do is you need to divide this term by this term. Okay, so that is y omega, this x omega. So you will have the xn. Okay, this value. Okay, so that is a omega value is there. Okay, okay, for example, I will take this as 1, this one 0. Okay, and this one 0. Okay, okay, and if you find the Fourier transform of this one, what is the value? Okay, x0 is 0, x2 is also 0, and you will have only x1. Okay, so you will have the value 1 e to the power minus j omega. Okay, e to the power minus j omega. And if you get this one, I will make this also 0. Okay, so y0 is 0, y1 also 0, y2 will be 1 e to the power minus j omega 2, n is 2. Okay, now if I have y omega divided by x omega, what is the value I have? I will have h omega. So that is what? Y omega is this one, e to the power minus j omega 2. X omega will be this one, e to the power minus j omega. So what is the value here? E to the power minus j omega, no? Because this one is reduced by this one, minus j omega. So this is the h omega. To find that, then what we need to do? What we need to do? So to find Hn, you need to apply the inverse Fourier transform to the h omega. So then you can find Hn, but to apply the Fourier transform, inverse Fourier transform, you need to do a integration, 1 over 2, 5 integration, e to the power minus j omega, e to the power j omega n d omega, no? Okay, so this integration you need to find within 2, 5. 2, 5 means 0 to 2, 5, you can find. Okay, within 2, 5, no? So just find it 0 to 2, 5. Okay, then you can have a value here. Okay, so this, so once you integrate this by omega, and if you apply 0 and 2, 5 to this omega, omega will cancel and you will have the value with n only. Okay, with only, I don't know, this is this can be integrated or not. Okay, so it seems it can be integrated because both are e to the power terms, no? Okay, so we have this so here we have e to the power minus j omega 1 plus n. Okay, so minus j1 plus n is a constant here, and if you integrate this, you will have e to the power minus j omega 1 plus n divided by minus j 1 plus n. Okay, then you need to apply 0 to 2, 5 limits. Okay, 0 to 2 5 limit. Then you will have, okay, so once you apply 0, so this term is this minus j1 plus n is a constant, okay, and if you apply 2 5, so it will be minus j omega minus j2 5 1 plus n uh, minus e to the power 0, so it will be 1 e to the power 0. This 0 should be applied to omega, so it will be e to the power 0. Okay, and I hope this will be 1. Okay, because once you find this, so you know that cos 2 5 plus j sine 2 5 will be cos 2 5 is minus 1, no, sine 2 5 is 0. Okay, so here maybe you have minus 1. Okay, I don't know. Okay, just check this, maybe you will have minus 1 here. Okay, so minus 1 you will have minus 2, so it will be 2 over j 1 plus n, maybe, not sure. Okay, just check it. Okay, I'm not sure. Okay, so that is how we apply the uh, convolution property. Okay, so please familiar with these one, linearity property, time shifting, time reversal, and this one. So we have done example for this one. Okay, and also I think this one also somewhat important. This one, this is we called as frequency shifting. Okay, because if the xn is multiplied by this kind of term e to the power j omega naught n, so the Fourier transform, okay, x omega will be shifted here, omega minus omega naught. Okay, so here the frequency shifting property. Okay, this is we call that frequency shifting property. Okay, so uh, please familiar with, at least familiar with these 1 2 3 4 5 linearity, time shifting, time reversal, convolution, and frequency shifting property. Okay, okay. So I think that will be enough for Fourier transform. Okay, then actually we have another part. Okay, we have another part.